Hope you all feel well. Class guy, Zoom guy, and the lecturer guy. Okay, we discussed the marvelous notion of partial derivatives. Fxi is the partial derivative of f by the variable xi. Basically, we consider all the other variables to be constants and differentiate um, properly. Oh, that's my words here. Differentiate by that way, by that rule, whatever. Okay. We discussed differentiability, the fact that we can use, huh? שירותים? כן, משמאל. We discussed possibility the fact that you can use the partial derivatives to form a kind of linear approximation to the function, which is basically the Taylor series of order one. We discussed Taylor series today, בלי נדר. And need one more thing to discuss about the derivatives themselves before we can move on. We discussed differentiability, the ability to use the partial derivatives form a linear approximation for the function f. Different angle to look at the derivative of one variable function is what you discussed, what you mentioned last week, how the function changes at one point. Yeah. Is the change or how the function changes at a point in order to generalize this aspect of the derivative. Okay. Just this aspect, two L's or just one L? I don't know. I think it's two. Whatever. Oh, aspect of the derivative, we use the concept of directional derivative. Okay, so this is our new headline. Directional derivative. When it comes to one variable function, the question, okay, which direction we go is irrelevant. It's always the right. The straight line, we go to the always go to the right. Let's write down in R. There is only one direction, right? If f tag at some point is a is greater than 0, then the function is what? Is increasing. Increasing when you go, we always go to the right, the axis goes to the right, and the function is increasing or decreasing, is increasing, or you can think of it as a decreasing function. We go to the left. Around A, and well, when we go through A, I don't know, and right down that way. When we go through A, and if f tag A is negative number, then the function is decreasing. Well, we know that. It's not a big news. But right now, right here, right now, for example, let's talk about R2. When we look at R2, this is what we discussed last Sunday about limits. We have standing at a specific point, we have like an infinite number of directions we can move forward to. You know, standing right here on top of my head, my head right here, so I can move this way, and this way, and this way, and considering my head to be a 3D graph of a two variables function. So saying that the function is increasing or decreasing is irrelevant. We have to consider the direction in which we go to. Okay, go to this direction, yeah, the function is increasing. You know, go this direction, well, the function is decreasing right there. And looking for example, the graph or something, a bit more precisely. Maybe the Wikipedia page has a nice animation. Nah, it's shitty. Didn't expect much. No, let's look together at some graph. I will draw myself. Where is it?
Yeah. Which color function two variables in the third dimension. So like
Yes.
for our representation, we always do an extra dimension to represent it.
Yes. All the axes for the variables and the function axis. Just like in one variable. Okay, this is the graph of x squared plus y squared. Do you use decimals or something, which is better? No, I just want to move it, you know. I like to move it. Open graphing calculator, yeah. A plot, does he understand what I want? No.
No, you can just say
fx1, yeah. X squared plus y squared. Do you copy Desmos? Yes, how do I put it into this?
I think it's the multi-range there, right?
What? This?
Yeah.
More options. More axis. And use the complex mode. Oh no.
Well,
Braille mode. I'm used to start to, you know, my computer. What the hell? Yeah, it's not that important. We can explain it right here. Say you stand in this point here on my graph where my cursor is. If we
if you want, go to the swap and change like from calculator in the URL to 3D.
okay. Yes, leave. Let me be. Ah, nice. Okay, so fxy is x squared plus y squared. I called it a paraboloid. And actually don't see the axis of the grid on it, but not very important. Woo, you can, oh, no. I just thought you can move it whatever you want. Okay, so looking at the very nice paraboloid here, let's say, and I can use the zoom to annotate even more, which is fine. Let's say I'm standing here at the origin and I'm moving in this direction on the plane. How does the function changes? It goes up, right? But on the other hand, if I'm standing here at this point, this is, for example, the point is here on the graph of the function, and I'm moving in this direction, then the function will decrease. Or stay the same if it's parallel, it will stay the same. So the question, how does the function changes? Depends in which direction we go. In order to mathematically form this, we need the notion of directional derivative. So in Rn, we first need to specify the direction in which we want to calculate the so-called change for the function. Formally, let f be a function of n variables. Let a and u be two points at Rn, and think of u as the direction and a as the point itself, or a stand. The directional derivatives of f at yeah. No, you want to save it? No. At a at the direction directed at you. That's how the we English Wikipedia says it. I don't know exactly how he calls it. Yeah, whatever. You know, in the direction of u is defined defined by how should I denote it? One can write it down as fu of a or something like that. And it is the limit of some little h goes to 0 of f plus hu minus fa above h. Now the definition is pretty intuitive, just like the regular derivative. I'm looking at the point A and I'm adding something very small at the direction of u. And I'm asking, you know what? How does the function changes when you move this little step along the direction of u? Just like in our graph. I mean, for example, let's say the point here is A, which is 0, 0. And we're looking at some direction. Let's say this is direction. Here is the point 1, 1, right? For example, it's the x and y axis. And I'm asking, oh, you know what? Let's take the point A and weight something a little to the point, this is u, to the u. How does the function changes? I mean, let's look at the difference between fa plus hu to fa. Now, of course, divided by age, as we are already used to. Now, an important thing to ensure is that the value of the directional derivative depends only on the direction of u and not on the norm of u. I mean, instead if u is big or small, it shouldn't matter. I should look at the direction of u and not at um, the norm of u. Yeah.
Not doing the other way around. We should look at the normal view because that's the direction of size one, or
Exactly. So we should um, have it as a standard or something like that. The vectors we use in calculate for calculating the directional derivative should always be normalized vectors.
that's why. No, I was going to ask, how can you know you're not affecting if you're not dividing by u, but you need to use some u that's of size one?
Yes. I mean, one can divide it by the um, norm of u and it will be eventually the same, but it's better to start with normalized vectors at the first place. Of course, we don't want, we do not want to be affected. It's with A, with E, whatever, by the norm of u. Only its direction is what matters to us. So we normalize u in our definition. So one can do it here instead of u. Just write u above u above its norm. And the rational derivative, the directional derivative describes the yet again change of the value of the function as we move from the point A in the direction u. Now, we can use this formula, it's very nice, but actually give you some theorem. Of course, we can use it, and as I mentioned before, I'm not going to prove theorems here in this part of the course. Theorem, if f is differentiable at the point A, then one can calculate the directional derivative pretty easily. Of course, depends on how you look at it. The normalized vector of u multiplied, you know what? We love linear algebra, especially linear algebra 2. You have like, the most handsome lecturer ever stepped in Parallel University. This is the inner product, this is the standard one, the one first by first, second by second, etc., etc. Between the normalized vector u and the nabla vector of a, which nabla I'll write down now explicitly. We've already mentioned him, but write down this specifically when nabla a is the gradient of f at a. What is the gradient? The vector of the partial derivatives. The gradient is the first derivative at the point A, the second derivative at the point A, and so on. Okay, this is a very nice formulas. Let's
So
yeah, let's have some example. Yeah.
we the functions that are multivariable taking multiple variables, or they can take a vector of that size, it doesn't really matter.
Mm-hmm.
U is a vector of one more dimension than that.
No, same dimension.
Um,
Same dimension of Rn. And the graph is one more dimension.
so when you take a direction it's like, for example, on the graph you showed, you took a direction of 2 dimensions.
Yes, in R2.
Which means it's only dependent on the plane and not on the.
That's right.
But that means, like, do they still have the graph?
Yes.
So you can't like say the direction from here. It has to be relative to the plane.
Yes, and you look at the image of the direction.
Okay. Okay.
Sammy, any questions?
Nope.
Okay, so let's have an example. For example, let, I don't know, f x, y, z be the following function, and x multiplied by arctangents y, z. Let's calculate. And now let A be the point of 1, 1, 1. And U be the point, the vector of 3, 0, 4. So the function is differentiable at the points 1, 1, 1. It is always differentiable because we know how to calculate its derivatives, and they are all continuous because it's an elementary function. And so we can use the formula with the multiplication with the inner product. Here, what are the partial derivatives? The derivative by x, yet again considering all the rest to be some constants, so 5x leaves us with 5. Derivative by y is more tricky. X is a constant. How do we differentiate our tangents? It's 1 above 1 plus the function squared. But we have to multiply by the inner derivative, you say in Hebrew, which is z here. I'm considering it to be some 5y or something. So multiply by 5, multiply by z. And the same for z. X is a constant. X is a constant. 1 above 1 plus the function squared multiplied by the inner derivative, which is y in this case. And so at our point 1, 1, 1, the gradient of f at the point 1, 1 is fxx at 1, 1, 1, fx fy at 1, 1, 1, fz at 1, 1, 1. And again, it should be z not x. And here, well, let me do it by hand, by my head. Arctangent 1 is pi above 4, above, not beside. Here, 1, 1, 1 above 1 plus 1, it is 1 above 2, and yet again, 1 above 2. On the other hand, U is 304, so the norm of U is 5. I chose a number, it should be integer. It's not necessarily always true. It's 5, so the normalized U is 5 with 304. You know what, for a nicer number, let's change it to 03. Maybe want this stinky pie to be here. 03. And finally, the directional derivative of a of f at a in the direction u is the inner product between the normalized u and the gradient of a, which is 5 with 0.34 and nice gradient. We are left with 5 with, okay, 0 and 3 above 2 plus 4 above 2, which is 7 above 10. Geometrically speaking, we cannot imagine this function. It requires 3 dimensions only for its domain and one additional, one extra dimension for the graph itself. 4 dimensions is pretty hard to imagine, not a lobster or something like that. I mean, I heard that I can see in something like 8 dimensions. Their vision is much more advanced than us. Still, doesn't help them to run away from the, from the fisherman. But we can say that as long as we standing at the point 1, 1, 1 and moving a little in the direction of 0, 3, 4, the function increasing. Is 7 above 10 is steep increasing or not so steep? Depends on the context. It's not a mathematical question, just as we said about approximation. Is having the remainder less than 1 above 1,000, is it good, is it bad? Depends on the context, not a mathematical question. Okay, this is the directional derivative. Let's write down this business. So we can say that the function is increasing when we move from 1, 1, 1 in the direction 0, 4. The slope, slippery slope, is 7 above 10. It's not a slope, it's the other way around, but you understand. Okay, I want to ask you a question about directional derivative, and then we can move on. And before that, any questions about what we discussed here? Okay. A legit question. We stand at the point with infinite number of directions to go through. In which direction should the change in the function, should the directional derivative be the maximum change possible? And what is this maximal change?
I mean, it depends on the function, right?
Of course, and the point and the directions. But we can go back to our graph. Let's shake it up a little bit to be more complex. Okay, so it's thinking. How do I tame this x third plus x squared multiplied by sinus? Okay, it's cheating. Let's say we stand at some point here. Okay, where's my annotation? We stand at the point here, not at the origin. No, let's say we stand at the point here. Okay, this is the point on the graph. Now, if we move here, the value of the function in the z-axis doesn't change much. If we move in this direction, well, we go up here. If we move in this direction, we go up here. It's not very up, but it's up still. So the question, in which direction we have the maximal change? And what is this maximal change is a legit question. Of course, we can ask it about the minimal change, the steepest and the slope and the slipperiest slope, all the same. So let's go back to the links. This proposition. Well, I can prove it. It's not very hard using Cauchy-Schwarz inequality. We measure the linear algebra too, but we don't have the time. Proposition, I miss the I here. Proposition Joe. Let f be a differentiable function at the point A. Then if we look at the maximum all above the vector u in Rn of the directional derivative of f at A, the maximal directional derivative is the normalized gradient of f at A, and we achieve this maximum is achieved at u when it is the gradient. We want to consider the steepest the direction in which the function has the steepest increase or something like that. You look at the gradient, and the directional derivative will be the normalized gradient. Why does it work? Well, we can use this formula because it's differentiable, and then using Cauchy-Schwarz, you can, as I mentioned, you can achieve that. I don't want to do it right here. Just let you know it is possible. And yes, we should, if we want to understand or prove, or more than just know the basic concepts here, we need to mix linear algebra and calculus. Uh, the proof. Not very hard. Using Cauchy words. Free proposal. Not important, don't be afraid. Be not afraid of linear algebra. When it comes to calculus, the person available. Yet again, and similarly, the minimum is the minus of the norm of the gradient and is achieved at the direction which is the minimum of the gradient. For example, in which direction the function, this arctangents, whatever, has the steepest slope, the function, this one has the steepest slope at 1, 1, 1. I mean, in Hebrew, slope is only midron when you go down, or is you can use it for the ma'ale, both? Okay. So steepest slope should be specified, if I mean the increasing or decreasing one, right?
Steepest, I don't think.
Yeah. Steepest? Okay. Oh, it's steep without the Y. Yeah. It's not steepy. Steep. Steepest slope at 111. It is, lol, it is the gradient at 111. Of course, we should normalize it. I can write down here. Yes, we should normalize it, considering a direction we mentioned before should be a normalized vector, and here as well. Should be normalized, yeah, whatever. And the this maximal sheave, the maximal change is the gradient, norm of the gradient, which is square root of pi above 4 squared plus half squared plus half squared. Whatever this number is. It's a legit question. Here's a function, find the direction in which the function is has the maximum change, or the minimal change, whatever. Okay. This was my take about the directional derivative, which generalized the concept of change of one variable function. What the derivative of one variable function. Note to how to say pretty easily, here we need some different notion, differentiability in directional derivatives. Okay. Any questions about that? So my next little subject, which will be regular, is Taylor. Okay, the Taylor series or Taylor polynomial about of multivariable function. Let's write down the formula, understanding that yeah, it is a generalized version of the one variable version, and move on. Taylor polynomial. Okay. So let in one variable for one variable function f, we know that the Taylor polynomial of f at a of order n is the following. It goes from 0 to n. The derivatives at k above k factorial x minus a to power of k. Well, we know that. Now, how are we going to generalize it to n the n variables, not just one. So the generalized formula is pretty ugly. I mean, should differentiate divide by many factorials and look at all the different um, derivatives possible. We talked about it last week. Some kind of combinatorial question, how many different derivatives there are. And so I want to write it down and use an example for, let's say, two variables and order two polynomial. And then I'll just write down the general formula for you to be odd. Okay, to be wowed. And when it comes to more than one variable, the formula is basically the same. Dividing the derivatives by the factorial and multiplying by the by monoms. Yes, monoms x minus a to the power of k. Problem is that we have many different partial derivatives, more and more uh, as we look at higher order. And the formula is pretty ugly. I want to write down, as I mentioned, for two variables, and then we can discuss the general formula. I don't think it's the best way to do it. That's pretty ugly. For example, the Taylor polynomial of fxy at the point a, b of order 2 is the following abomination. P2xy, first of all, is f itself, right, at the point. And then we add the first derivatives multiplied by the corresponding monoms, fxab, as we say, fyab, y minus b. And then we need to write down the second derivatives, which is fxx at the point multiplied by x minus a squared, and fyy at the point by y minus b squared. Of course, we should divide it by, you know what, if it's divided by 1 factorial, and it is 1 factorial to the power of 1. It is divided by 1 factorial to the power of 1. And here we discuss the terms of second order, so they should be divided by 2 factorial. Oh, and here 2 factorial as well. Again, with fxy, the point above 2 factorial, and because it is y, you should be multiplying by x minus a 1 and y minus b 1, and by Allah, you should add the second derivative of yx, which be the same element. Now we considered we consider our functions to be functions with the same second order derivatives. fxy and fyx are the same. We talked about it last week. If they are continuous, but by our examples, every function is continuous, so it should be fine. So writing it down more explicitly, we achieve this one soothing formula, or should be multiplied by 2. It's still pretty ugly. It's only 2 variables and order only 2, not an order 50 or something like that. Huh? Yeah, it's pretty ugly. I will show, maybe I'll just, just share my screen with you or something like that. It's pretty ugly, yeah. But let's go for an example. For example, and then for the formula, then we can move on. Just using the examples, not so important for me. For example, we find P2 at a point, let's say 1, 0 of the function f, which is square root of x squared plus y squared. Okay, so we need to find the first and the second derivatives at the point 1, 0. So fxy is x squared plus y squared to the power of half. It's easier to differentiate it that way. So
I don't remember why, and I don't think I care either, but
what?
like doing this, the square root and the power of 1/2 is different somehow, but like I didn't really remember why someone said it.
I don't know why. It's just a notation.
Yeah.
The square root, I mean, is just a notation. Okay, so at our points 1, 0, it is just 1. Now the derivatives, the half is going out there, and we are looking at minus half here, and it's multiplied by the inner derivative, which is 2x. As is practically the same for y. That's the inner derivative is 2y and not 2x. So at the point 1, 0, we do get here 1 as far as I can see. And when you put 1, 0 in the derivative by y, it is just 0. Now, second derivatives, we should differentiate that by x all along. It is that 2.5 cancel each other. Now it's x multiplied by this one, so it's a derivative of multiplication. The derivative of x is 1 multiplied by that, and x multiplied by the derivative of the power, which is minus half multiplied by x squared plus y squared. So at our point, this is 1, and this is minus half, so it is half, as far as I can see. Check me before check myself or correct myself, right? Yes, is it? Is that so? Something's wrong. Is it wrong? No, I think it's okay. The half is going down, and yeah. But this one here plus x multiplied by... I missed the inner derivative here, which is yet again 2x. That's what I missed. And with the 2 here, it's 1 minus 1, which is 0. Okay. Now, by y, it should practically be the same, just with y as the inner derivative. And it is 1. This one becomes 1. This is 0. One big fat 0. And fxy, which is fyx at 1, 0. Differentiate that by y. So the x is just constant. Multiply by this with -3 above the 2. And multiplied by the inner derivative, which is 2y. In this case, so the both of the partial derivatives fxy and fyx at the point 1, 0 are 0 because the y is 0. I mean, no complaints, right? More as 0 as we can. And we have finally the P2 is this marvelous formula, which is actually 1 plus 1 multiplied by x minus 1 to the power of 1, plus 1 above 2 factorial, y minus 0 to the power of 2, which is 1 plus x minus 1 plus y squared or something like that. Okay. It's a very nice way to put it. An approximation, as usual. This one is a quadratic or something like that. Approximation for the function at the point 1, 0. Tell me any questions about that?
Nope.
Okay. So first of all, as I mentioned, we can write the formula for the general case. I don't think we want to do it. And secondly, we can do whatever we did about Taylor series eponymas of one variable. I mean, finding the polynomial or the series using an already known series of some derivatives using the series. The derivative should be the coefficient of blah, 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 and it is 0, it is 1, it's n factorial, whatever. Everything we did in one variable, we can do it here, but we are short of time, so I think maybe, just show you the formula, which is extremely ugly, and then we can move on. You know what? Let's write now as a note. The general case, the formula of Pm, order M, of f of n variables at some point A is nasty, a bit. Pm of x to xn is, you know what? Nah. It is ugly. It's one above. No, I already reading down right here. Maybe you already seen this kind of expression used talking about combinatorics in discrete mathematics. The way of doesn't matter. Not combinatorics lesson. And then we should look at the derivative of k1 times by x1, k2 times by x2, and so on. We cannot use this kind of notation. We need to use the snail one we mentioned last week. Yeah, we look at the n partial derivative of order n, but we differentiate k1 times by x1 and k2 times by x2. I write down in English, just by the way. Xn, Kn, and then we should multiply it by the point at the point A, so the derivative of the point A, and x1 minus a1 to the power of k1 multiplied by x2 minus a2 multiplied by to the power of k2, then x n minus an to the power of kn. And of course, we should look at the sigma here. So we run on sigma, 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 sigma every point from k1 to kn, which goes to m. I should be more specific. The sigma is not going, I mean, I cannot take each one of them to be m. For here, if I take both indexes to be 2, then it's the derivative of 4 order. The differentiate 2 times by x, 2 times by y. It's the derivative 4, not 2. So the sigma is more delicate. It's about calculating the sigma. I mean, if it's you look at the Taylor series, then every sigma goes to infinity and it's totally fine. But here, when we talk about the polynomial, we don't want to look at derivative of order higher than m. And for my example, let's say m is 2. I cannot differentiate 2 times by x and 2 times by y. It would be derivative of order 4. So more precisely, and that's how I write down, it's looking at the following sigma. When we look all over the options of k's, in which their sum is m. So here in the two variables and m equals 2, we have 3 options for the derivatives. In total order of 2. You can differentiate 2 times by x and 0 times by y, which is this element. You can differentiate 2 times by y and 0 times by x, and you can differentiate 1 time by x and 1 time by y. But you could do it twice, xy or yx.
Yeah, but that's different operations.
Yes, so where this abomination is the partial derivative of f at a, k1 times ki times by xi. No, you know what? Something's wrong here. I mean, here you look only at the elements of order m, but the Taylor's polynomial is all the elements of order less up to m, exactly. So it should be less or equal. And of course, where k's are factorial, integers, non-negative integers, meaning minus 1 plus 1 or something like that. By xi at the point A. The sum goes over the options of derivatives of order less than m. Let's say now, which word? Let's say k less than m. For example, for two variables and 2 m equals 2, we have three options, or actually four. Differentiate 2 times k1 equals 2 times by x, and k2 times 0 by y, and vice versa. Differentiate 1 time by x and 1 time by y, and vice versa. Now, actually, as we mentioned before, fxy and fyx are the same. So you only see three options here, but there are actually four. That's why it's multiplied by 2. Now, it's very ugly, as I mentioned, and considering the Taylor series is sum k1 runs from 0 to infinity, k2, it's sum over sum over sum over sum. Pretty ugly. I don't think, of course, I'm not going to ask you about it in the final exam or something, but I don't think you actually need it, or at least to study it right now in order to succeed in your next courses or at your job. The second thing I want to write down, then the questions, then we move on. Um, second thing. Second thing. We can ask the same questions as we asked about one variable. For example, finding the polynomial using known polynomials. Finding a specific partial derivatives using the right coefficient of the polynomial, and so on. I mean, for example, I don't want to waste your time, but I'm wasting it already, so why not? 6 lectures is not enough. I need 7 for the multivariable. Calculus, it's not your problem. If you miss something for syllabus, it's okay. We won't appear in the final exam, of course. But for my next semester, for semester bet, I should take notes. I don't know, for example, let's say I want to find we want big E. We want to find P, let's say 5xy of e power of x sinus 2y of at 0, 0. The Maclaurin one. So we can use this formula, but when it comes to the partial derivatives of order 5, even though it's only two variables, we have it's not a lot. I mean, but still 5 times x, 4 times x, and 1 time y, 3 times x, and 2 times y, and so on. And we need to calculate how many times we have each derivatives in order to put it here in this monstrosity. So the easy way to do it, no, easier, not easy, is to know, we know that, let's use it with x, no, let's use it with x squared. So be easy. We know that ex squared is looking to of order not more than up to 5, not more than 5. It is 1 plus 1x squared plus, I mean, let's write down explicitly. Ex is the sum of xn above n factorial, and we know that sinus 2y, sinus y, begin with, is the sum of minus 1 to the power of n, x 2n plus 1 above 2n plus 1 factorial, right?
Yeah. Why? Okay.
And yeah, of course. So, e to the power of x squared is writing it down only to the requested power, which is 5. It's x2n above n factorial, which is prox 1 plus x squared plus x4 above 2. And Mr. Sinus is the sum with 2y. That yields the first element is 2y, and then it's minus 2y to the power of 3 above 3 factorial, which is 6, and 2y to the power of 5 above 5 factorial. We get that the desired polynomial is, why aren't you, what? Why?
Because E is part of the function.
Yeah. How is it? No, all it's different as the other way around. The function is part of the E here. Weird leaks. It's weird copy paste methods. Mechanics. It is approximately P5 here. I use the small p instead of big P, so fine. Which is the multiplication of this one and that one. Why did I write it? Why did I write it with another approx? Because if we look only at the elements of order not greater than 5, we don't need all the elements achieved from this multiplication. I mean, x to the power 4 multiplied by y to the power 5 is an element of order 9. Not looking for it. I'm just using the polynomials of order 5, and then I let go of all the high order, too high order the elements. What are we left with here? It's 2y. All this multiplied by 1.
P5 is just the error polynomial of 5, or
Of order 5. And specifically here is the Maclaurin one. I mean, let's write down a bit differently. Take it from here. X squared. And who did I miss? It's 2y multiplied by x to the power of 4. The other elements, this is the approximate. and this is the P5. The other, you told me we called it multiplicants, right? Multiplicants are of orders higher than 5, then with A, and we do not write it because they ask us for order 5. So instead of calculating all these exhausting derivatives using this abomination monstrosity of formula, we can just use our known series. Okay, any questions about that?
Um,
Yeah.
so how how do we know when to stop when we are taking two functions that are not the original one? Like we have e to the x squared on one side and sinus to y on the other, and we decided to do p3 for them.
Yes.
So how do we decide when to stop?
No, it's not P3. It's both of them do have 3 elements, but this is P4, or more precisely, P5. It's all the elements up to order 5. And this is similarly for sinus. And yet again, when we multiply all the elements here of order up to 5 and all the elements here order up to 5, we do achieve elements of orders higher than 5. And if we want P5, we don't need to write it down. Oh, don't need, and we shouldn't write them down. Okay, Sammy, any questions?
No, I'm good.
Okay, so for my last trick, as I mentioned, I didn't plan the time well. You will be fine, but for next semester, I need 7 lectures, not 6. 7 lectures. Chain rule. Okay, what do we know about one variable? In one variable, the derivative of f at some point gx or ga instead of a is the derivative of f at ga multiplied by what we call the inner derivative g tag a. You know that we do it all the time, including right now. What happens in more than one variable? And here it's a bit tricky. Even considering that the functions take some number larger than one variables and gives us back one variable, not function from Rn to Rm, or just function from Rn to R. Here we can talk about function that has an input of n variables, and each one of these variables is itself a function of, say, m variables. So the basic formula should be the same. The outer derivative multiplied by the inner derivative. When we trying to find derivative of the outer function by the inner, means this derivative, right? A little bit more precise, of f. No, it's not. It should be circ at a. Yeah. So we generalize it. That's right. It's with 2 L's or just 1 L. Generalize. No, it's 1 L. Fuck. Yeah, I was just it's going on the 2 L's here all night long. Maybe it's in British English something. New Zealand English, it's 2 L's. You can never know. I probably normalize it with 1 L. Yeah. Can I look for double L's here? Fine. Yes. Finally, it's good with 2 L's, right? Normalize. No, it's 1 L. Fine. Where are you? Basically, it's 2 L's. It's still fine. The end of search. Yes. But the beginning. Basically, it's good. All generalized. Yeah. 1 L. Formally is good. Finally is good. Okay, we did. We generalize it as follows. Let f be a function of n variable, f of x and x to xn, each of which is a function of, say, m variables. So we have f of x, which is actually u2 to um and x2 and so on till xn is a function of u1 to um. And I mean, f and x are all differentiable, okay? Where f is differentiable at the point x1 to xn, and xi are all differentiable at u1, then the function is differentiable, blah, 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 and the partial derivative of f by ui by the inner variable is f by x1 multiplied by x1 by ui. Let's write down x1 derivative by ui. But it's not only x1. It's x2 and x3 and so on. So it's a nice little sigma here when we differentiate f by the variable, and then differentiate the variable by the inner variable. So it's a nice formula. Let's have some example. I mean, I have examples here. I'm going to teach Infi 3 for mathematicians, but this is a more complicated one. We're using matrices, functions from Rn to Rm. Let's do something. Where are you? No. Let's get an example for my head. For example, we find f by u, where fxy is the function x squared y third plus 6y, why not? And x is function of u and v is the function uv, while y as a function of uv is the function, let's write it down as no, ln u plus v squared, whatever. So on one hand, we can write f as a function of uv explicitly. F of xy is x squared y third sinus y, which is uv squared ln u plus v squared third plus sinus of ln u plus v squared. And we can find f of u using this function. And we know how to find fu. Might be ugly, but it does work. On the other hand, we can use chain rule, the derivative of f by u is f by x multiplied by x by u plus f by y multiplied by y by u, which is by x is 2x y third multiplied by x by u, which is v, plus f by y is 3x squared y squared plus cosinus y multiplied by y by u, which is 1 above u. And we can write here, instead of x and y, their functions, their expressions as u and v functions. I mean, it's 2, x is uv multiplied by y third, which is this one to the power of 3, u plus third, whatever, multiplied by v, plus 3 multiplied by uv squared multiplied by ln u plus v squared plus cosinus of ln u plus v squared multiplied by 1 above u.
Your x and y are functions.
Yes. The middle management.
So you have a f, which is a function
Of two variables, and each of which is a function itself of two other variables. Now, it's not always 2 and 2. It could be 2 and 3. That's why I write down with u with n and m in the general case. But the basic concept, as usual, is the same. You multiply the inner derivative by the outer derivative. You just have, happens to be a lot of them, so you sum. And Taylor, the ugly abominational monstrosity, is basically the same as one variable. All these factorials and derivatives and monoms. And the rational derivative is the same as derivative in one variable. This becomes uglier and sometimes linear algebra. It is what it is. Okay, any questions? More questions? Sammy, questions?
Yeah, I'm not getting this that much.
Okay.
Like,
Uh,
like I'm struggling with all the different variables being thrown around.
First of all, this is my formula. That's the calculating derivatives here is easier than here because it's easier to find derivative of this one by x or y and these by u and v instead of this one by u and v directly, but it is possible. After we find derivatives by x by y by u by v, instead of x and y and x and y and y, we substitute what they actually are by u and v. I mean, x is uv and y is ln u plus v squared. So instead of x, I write uv. Instead of x, I write uv. And instead of y, we write ln u plus v squared.
Right, so it's basically just substitution.
It's at the end, it's substitution. But the first step is differentiating, finding derivatives. But what we do is first of all differentiating each function by its own variable using my formula, and then we substitute. As I mentioned, we can do it the other way around. We can substitute the expressions of u and v instead of x and y, and then differentiate directly by u. But here it will be uglier. I mean, let's say I want to find derivative of this by u. It's a multiplication, and every power goes out and multiplying by the inner derivatives. It is possible. It's not extremely difficult, but it is easier to first of all differentiate and then substituting. And the chain rule helps us here. in this case.
Okay, I'm not sure what you differentiated there.
We have the case is called the middle management. We have a function of variables, and these variables are actually functions themselves of other variables. So we have middle variables and inner variables, and the outer function. And we want to find derivatives of the function by one of the inner variables. So how do we do it? Going through the middle variables. Just like the one variable case, in which we want to find the derivative of f at a, but with g in the middle. So it's f tag at g multiplied by g tag. It's basically the same here. If we have variables that are functions of other variables, we want to find derivative of f by one of the inner variables, then it is the function we differentiate it by the middle variable, just like we differentiate f by g here, and then multiplying it by the derivative of the middle variable by the inner variable, just like we multiply it here by the derivative of g at a, at the inner variable inside the second pair of brackets. So in our example, we have f of two variables, x and y, whatever it be. And x and y are both functions themselves of different variables u and v. So here the inner variables are u and v. And for example, we calculated the derivative of f by u. So fx xu, fy yu, and the derivatives here are of f by x and y, which is easier. And derivative of x and y are by u. And then we substitute x and y to be whatever they are in the language of u and v. And this is my final answer.
Okay, I get it. Nice.
Okay. So I wanted to, well, we will not, yeah, another topic, the local extrema. But it's all fun. We'll do it on Tuesday. Then move on to extrema, global extrema. See how we finish our semester. So Sammy, you stay safe. Thomas, you as well. And may we meet on Tuesday.
Amen.
Amen.